one derivation. You need not to learn this derivation, but after this derivation, we will write one note. If you want to understand that note, you have to see this derivation carefully. ये नोट लिखेंगे, उस नोट में एक फार्मूला लिखेंगे, उस फार्मूला को डेरिवेशन करेंगे. डेरिवेशन देखते रहो आप लोग, वो फार्मूला याद हो जाएगा. देन वो फार्मूला को कैसे यूज़ करना है क्वेश्चन सॉल्व करने में, वो आसान से समझ में आ जाएगा आपको. ये बिना डेरिवेशन से आप लोग फार्मूला सीधे लिखेंगे, बहुत मुश्किल हो जाएगा. So now I am writing the question. The question is, find h bar, that means magnetic field intensity, in all regions due to, all regions means in the rectangular system point xyz, in cylindrical system point rho pi z, in spherical system point r theta pi, like that, due to I current going in a finite long line, going in a finite long line along z axis from point A to point B as shown below. This is y axis, this is x axis, this is z axis. Now here let us say this is location A, 0 0 z dash of A, and this is location B, 0 0 z dash of B. Here current is going like this. It is given I current is going in the finite long line. Finite means thoda sa length hai. That is from z dash A height to z dash B height. For example, 2 meters to 10 meters, let us say. Then z dash A is 2 meters, z dash B is 10 meters. Like that. So let us start this is the question. Let us start the derivation. H bar is required in all regions. We will solve this line question in the cylindrical system. In cylindrical system, all region means rho pi z location. You want h bar at rho pi z location, that is called as point 2. Now select small length on the current line. So what we do, this is z is equal to 0. At z height we will select small length called dz. It is common sense, student. On the x-axis, small length means at x distance we will select dx, small distance. On the y-axis, at y distance we will select a small length called dy. On the z-axis, at z height we will select dz, differential length. So dz is selected here. Now at which location you have selected this small length, that is called as point 1. So on the z-axis, x value 0, y value 0, at z height you have selected, so that is z. So this is the point 1 location where small length is selected, and you want h bar at point 2 location. If you see carefully, this is x-axis, this is y-axis, so this is xy plane. From xy plane, height of this field point is z I have taken. Now here also I have taken z. You can't take same parameter for different heights. This is different height, that is different height. We have to change one parameter. So I am taking this as a z dash height. Then at z dash height, I have selected here replace z with z dash. So here dash symbol is used for source location, current source location. Simply z height is used for field location. Now here R12 bar means like this, R12 bar. That is field point. I want field here. So field point minus source point. So here students, we are solving this in cylindrical system. This is rectangular system point. This is nothing but in cylindrical system. This point is nothing but if 0 pi z dash we can take. If radius is 0, then angle can be any value. So that x is equal to rho cos pi and y is equal to rho sin pi. Now here angle is a pi, but radius is 0. If you put radius 0, you get x0, y0. So this is rectangular system, this point, and this is in cylindrical system because we are solving the problem in cylindrical system. So if rho is 0, then any angle it may be, then x value, y value 0. So this is in a rectangular system. So in this way, now this is in cylindrical system, you can write this as this location as a 0 comma pi comma z dash. You can use conversions if you have any doubt. Okay. Now rho minus 0 into a rho cap, pi minus pi cancel, z minus z dash into az. For field point height is z. For this current source point height is z dash. So now R12 bar is equal to rho a rho plus z minus z dash az. Here dl1 bar is equal to, at point 1 location differential length is dz dash, and that is along z axis, so az. So dear students, on the z axis I am writing here once again, on the z axis differential length equation is dz az, that everybody knows on the z axis. Now in this question, at point 1 location differential length is required, so dl1 bar. At point 1 location differential length is dz dash az. Actually if you write R12 bar, automatically almost derivation will be over, simple mathematics will be there. This is the toughest part in the derivation. Anyway, now Biot-Savart law says dH12 bar is equal to I1 dl1 cross R12 bar divided by 4 pi modulus of R12 whole cube. Now let us substitute here how much current is going, I current. dl1 bar is dz dash az cross R12 bar is rho a rho plus z minus z dash a z. Okay, divided by 4 pi. R12 bar is this one, modulus of that means rho square z minus z dash whole square, that is modulus of R12, then whole cube is there. You know that in cylindrical system, a rho cap, a pi cap, az cap, they are in the sequence. Already you know this in the basics. Now az cross a rho, so az cross a rho is required. So az cross a rho is a pi. Next az cross az is 0 because cross product between same unit vectors is 0 actually. So from this dH12 bar is equal to I into dz dash into here rho into az cross a rho. Az cross a rho is a pi. Then az cross az is 0 divided by 4 pi rho square z minus z dash whole square root whole cube. What is total h bar? Total h bar is integration. So total h bar is integration of that I dz dash into rho a pi divided by 4 pi rho square z minus z dash whole square whole cube. So here z dash is integration variable. For location A, z dash is varying from z dash A, and for upper point the height is z dash B. So dear students, the integration from z dash A to z dash B. Now in the mathematics, integration variable z dash is in the denominator. It is difficult to integrate. That is why we take angles. So let us go to the angle terms now. Before going to angle terms, I will readjust this equation. So here h1 bar, h12 bar is equal to integral z dash variable varying from z dash a height to z dash b height, then I into rho divided by, anyway I will write dz dash a pi 4 pi. This is nothing but modulus of r12 whole cube only. Once again I am writing this as a mod r12 whole cube. So I will adjust this equation. I by 4 pi I is constant, it came out. Then integral z dash varying from z dash a to z dash b. If you want angles na, then distance by distance, current by current, because angles doesn't have units. Cos pi, sin pi, tan pi, they are ratios, they don't have unit. So that is why you write this in terms of distance by distance like this. So I by 4 pi came out. So distance rho divided by modulus of r12 is also distance by distance. Then here if you write mod r12 here, then remaining is mod r12 whole square is remaining. Okay. So I will write thick, little bit thick. So rho divided by mod r12. Okay. Then I by 4 pi came out, rho by mod r12, then whole square is remaining, then a pi, then dz dash in integrals na, dz dash dx, that is written here. So now we will write this equation 1 um, in angles terms. For that we have to redraw the first diagram. I will redraw here. दोबारा और एक बार ड्रा करना है. So here let us take, this is z axis. Okay, capital Z means z axis. Now this is y, this is x, and here from z dash a height to z dash b height, that current was going, I current. You have selected dz dash at z dash height actually. This is at which height? Z dash height it is. So this is at z dash height. Now just I have mentioned here height, student. What is this height? Z dash a. What is this height? Z dash. What is this height? Z dash b. Now here there is one point called point 2 rho comma pi comma z. Can you tell me What is this? R12 bar. Then what is the magnitude of this distance? Modulus of R12. What is rho? Rho is perpendicular distance from z-axis to this point. That is rho. This is perpendicular distance. What is z here? This is the x-axis. This is xy plane. From xy plane to this distance, from xy plane to this location, height is z actually. Small z, student, don't confuse here. Small z is height here. Capital Z is axis here. So I will write axis, z axis I will write, so that you will not confuse. Can you tell me what is this distance from here to here? This distance is this is z height, this is z dash height. Always these heights are measured from the origin. From origin to this the location height is z. From origin to this location height is z dash. So this distance is z minus z dash. This is mod R12. Now here some angle is there. I am taking this angle as a alpha. You can take theta also. You can take any parameter, alpha, theta, like that. I am taking alpha as the angle. Now, if you see carefully here, one by one, we want to convert rho by mod R12 into the angle terms. I am writing that here. Rho by modulus of R12. If I take angle here, this distance is touching this angle, so it becomes adjacent. This is opposite to that angle, so this is opposite. This one is called hypotenuse now. Opposite to 90 degrees is hypotenuse in Pythagoras theorem. So here rho is adjacent, then this one is hypotenuse. That is the definition of cos. So cos alpha. So cos alpha is equal to rho by mod R12. From this mod R12 is equal to rho by cos alpha, that becomes rho sec alpha, secant. Now you have written rho by mod R12 as cos alpha, modulus of R12 as rho sec alpha, mod R12 whole square means rho square sec square alpha you get. Let us write tan also now. Tan alpha definition is opposite by adjacent. So opposite here is z minus z dash, adjacent is rho, opposite is z minus z dash. That implies z minus z dash is equal to rho tan alpha. Here in the integration, z dash is the variable, z dash, this z dash is varying from, for point A z dash A, for point B z dash B. So here z dash is variable. If you vary z dash, then angle also varies. So this is the variable now. But field location is constant. For example, if anybody asks me, I want field at 3 meters 60 degrees angle, then 10 meters height, then this rho value and z value is fixed, and for this line this z dash height is changing. Then if this z dash height, for example I am putting here, this z dash height changes, then this angle also changes. You differentiate this with respect to z dash, then this is constant, so 0, then this is 1, then rho into secant square alpha d alpha divided by dz dash. From this you get dz dash is equal to minus rho, send this minus here, minus rho 6 square alpha d alpha. Now let us substitute all the things in equation 1. Substitute angle terms in equation 1. Then h12 bar is equal to I divided by 4 pi integral rho by mod r12 becomes cos alpha, a pi is the direction, divided by mod r12 is this one, whole square means rho square 6 square alpha. Then dz dash is here, dz dash is minus rho 6 square alpha d alpha. Then here z dash height is there. At z dash height, the angle is alpha. That means we are changing z dash variable to alpha variable, angle variable. If you change z dash, then this line also moves so that alpha changes. Now, if z dash is equal to z dash a, then this line moves here. If z dash is equal to, if z dash height is equal to z dash a, then this line moves here. For example, let us say z dash a is equal to 2 meter. This is a constant height. Then this angle also become constant. Let us call that angle as a alpha a angle here. This angle. So now this angle becomes alpha a. If any student ask me what is alpha a, then simple students. So here tan alpha is equal to z minus z dash divided by rho. If you want alpha a, then in place of z dash you have to put z dash a height. In that way you get alpha a angle. Similarly, what happens if z dash height becomes z dash b, then that line moves here like this. So z dash is equal to z dash b height. Then this height is, let us say, 10 meters. That 10 is fixed. This line is also fixed. Then this angle also fixed. That angle I am calling that as a alpha b angle. So these heights are fixed, then angles are also fixed. That is alpha b angle. If any student asks me how to find alpha b angle, then here tan alpha is equal to z dash z minus z dash divided by rho. If z dash is variable, alpha also variable. Whenever z dash becomes z dash b, then that angle becomes alpha b. From this equation you can find alpha b angle. So now secant square cancel, rho also cancel, one rho remains in denominator, minus comes outside. So minus I divided by 4 pi rho integral, this is cos alpha, d alpha is there, then alpha varying from alpha a to alpha b, and a pi is remaining here. So dear students, rho cancel, one rho remains and minus came out, then cos alpha d alpha and alpha a to alpha b, a pi is there. So minus I divided by 4 pi rho integral cos alpha is sin alpha. So alpha varying from alpha a to alpha b, a pi cap. Now ultimate formula h bar at rho pi z location is equal to sine alpha b minus sine alpha a. Minus is there, so I divide by 4 pi rho sine alpha a minus sine alpha b into a pi cap. Now we got this formula, and I am going to write this formula in the note. So you have to understand everything. Before writing note, I will explain everything. Here I is magnitude of the current. Rho is a magnitude of perpendicular distance. This is 90 degrees means perpendicular. Magnitude of perpendicular distance from the z axis to this location. But what is there on the z axis? Current line is there. So that is why rho is a perpendicular distance from current line, that means z axis here, current line to the field point. But even though current conductor is up to this location, you have to extend that, then this is all called as current line. So rho is perpendicular distance from current line to the field point. Then tan alpha a, how to find alpha a? This z minus z dash a by rho. Rho is a perpendicular distance from current line to the field point. Then z dash a is a lower distance of the conductor. Actually, student, for example, it is 2 meter to 10 meter, let us say current is going. 2 value is lesser than this 10. So z dash a is lower distance and z dash b is higher distance of the conductor. Actually, if you want to solve any question, then you take the conductor. For example, conductor length is given from 0 to infinity. Current is going. Maybe current going like this or like this, doesn't matter. This is lower distance, that is taken as z dash a. This is higher distance. For example, current is going from 0 to minus infinity. Then 0 is lower distance. Minus infinity is lower distance. Then 0 is higher distance. So in that way, negative distance is taken as a lower distance. Then this is higher one. Here it is lower distance and this is higher one. Now you may get doubt, for current going like this, then current going like this, what to do? What we are doing here, we are going to generalize this formula. I am going to generalize like this. I by generalize means use same formula for all cases. That is the meaning of generalization. Generalize. सबको वही formula use करेंगे. Here a cap means unit vector, suffix h means unit vector in h bar direction, because we are writing a h bar formula. So now what is the formula of AH cap? A cap means unit vector, suffix h means unit vector in magnetic field direction. This I am going to write this AH cap. A cap means unit vector. A cap means unit vector. A cap means unit vector. Suffix h means unit vector in magnetic field direction. Then suffix I means unit vector in current direction. Then suffix perpendicular means unit vector along the perpendicular line. I will write that. Then cross product I am taking. You will ask me how you got this one. I got this one from the Biot-Savart law. Biot-Savart law says DH12 bar is equal to I1 DL1 cross A12 divided by 4 pi modulus of R12 whole square. Here H bar direction is equal to current direction cross unit vector along the perpendicular line drawn from current line to field point. From Biot-Savart law I wrote this one. Now what is AI cap? Unit vector in current direction. For example, current goes upwards. Then in place of AI cap, I will take AZ cap. If current goes in down direction, then in place of AI cap, I will take minus AZ cap. So current goes upwards, then I will take AZ cap. Current goes downwards, I will take minus AZ cap here. So maybe current going upward, maybe current going downward, then I will take this as a lower distance. I will take for both cases, I will take this as a higher distance location. But if current goes upward, then in the direction change is there, plus AZ, current going upward. Current going downward, then I will take minus AZ. But current going upward or downward, for both cases, I will take lower distance to find alpha A angle and higher distance to find alpha B angle. Now what is A perpendicular? I will do like this. I will find the perpendicular distance vector. So this is perpendicular, I will write in the note actually, just I am explaining now. This is perpendicular distance vector from current line to the field point. Then if I take modulus of this, then I will get perpendicular distance. Then if I take modulus perpendicular vector divided by a modulus of perpendicular vector, this gives A perpendicular, because perpendicular distance vector divided by modulus of perpendicular distance vector gives perpendicular unit vector. So I will be writing all these things in the note. Okay, students. How to find perpendicular vector? Already we have solved that in the electric field equation. We have solved that. If I solve one question, then you will understand. Don't worry. Even if you have forgotten, you will be recalling while solving the question. आप अगर भूल गए होगा टेंशन मत लो, क्वेश्चन सॉल्व करने में वो समझ में आ जाएगा आपको. ये फार्मूला को मैं यूज करूंगा इन्फिनिटी लॉन्ग लाइन के वजह से एच बार कैसे फाइंड करना है वो यूज करूंगा. उसके बाद मैं क्वेश्चन उसके बाद मैं नोट लिखूंगा. तो उस तरफ अभी इन्फिनिटी लॉन्ग लाइन के लिए सॉल्व करूंगा मैं. आप देखिए इधर, उसके बाद नोट लिखेंगे. सो इधर कंटिन्यूशन में चल रहा है स्टूडेंट्स. वो जो डेरिवेशन में फॉर्मूला है उसको इन्फिनिटी लॉन्ग लाइन के लिए यूज करूंगा. ठीक है. अगर एच बार चाहिए इन्फिनिटी लॉन्ग लाइन में करंट जाने की वजह से, सो ये माइनस इन्फिनिटी है, ये प्लस इन्फिनिटी है, करंट जा रहा है अभी. सो ये है नेगेटिव डिस्टेंस, मतलब लोअर डिस्टेंस है ये. पॉजिटिव डिस्टेंस मतलब हायर डिस्टेंस है ये, जेड डैश बी है वो. सो इसके लिए tan alpha A is equal to z minus z dash A divided by rho. इस केस में भी मेरे को चाहिए h बार चाहिए at rho pi z लोकेशन चाहिए, सेम लोकेशन में चाहिए. ठीक है. सो tan alpha A is equal to z minus z dash A divided by rho. So in field point height is z, field point radius is rho. Z dash A is minus infinity now. So that means I got here plus infinity plus z is infinity. Infinity divided by rho is infinity only. So that is nothing but tan pi by 2. So students, here alpha A, tan alpha A is equal to tan pi by 2. So alpha A is equal to pi by 2. Similarly, tan alpha B is equal to z minus z dash B divided by rho. So z minus of z dash B is infinity. So that is z minus infinity is minus infinity. That means that is actually tan minus pi by 2. Okay. So here alpha B is equal to minus pi by 2. Okay. Now if you want AH cap, that is equal to AI cross A perpendicular, I told you. Here directly current is going in Z direction. So AZ cross. A perpendicular means this is actually 90 degrees line. Along this in cylindrical system, arrow cap is a perpendicular unit vector. Directly I wrote what is perpendicular unit vector from Z axis to this field point in the cylindrical system, that is arrow cap. So now AZ cross arrow is A pi. Here you can see na AZ cross arrow gives A pi. Now let us substitute this in the formula. The formula is h bar is equal to I divided by 4 pi rho sine alpha A minus sine alpha B into AH cap, that is equal to I by 4 pi rho sine alpha A is pi by 2, so sine pi by 2 is 1 minus of sine alpha B, so alpha B is minus pi by 2, so sine minus pi by 2 is minus 1 into A pi cap, AH cap is A pi cap. So this is 2 to cancel, you got I divided by 2 pi rho A pi cap. Now I have done derivations. You need not to learn these derivations. Now I will write the results in the note. You have to remember them and you have to use them in solving questions. अभी तक मैंने derivations किया है, आप लोग ये derivations बिल्कुल सीखने की जरूरत नहीं है. वो derivations को मैं अभी नोट में लिखूंगा. जो नोट में लिखता है उसका स्टेटमेंट्स भी लिखूंगा, उसको अच्छे से याद रखना है और क्वेश्चन सॉल्व करने में यूज करना है. मैं क्वेश्चंस भी सॉल्व करूंगा, ठीक है. अगर what is the h bar due to infinity long line? Answer I divided by 2 pi rho A pi cap. That infinity long line is along the z axis, then A pi comes. But infinity long line is along the x axis, along like this, along the y axis. Then what happens? Current divided by 2 pi rho will be same. Then AH cap is replaced with A pi cap is replaced with AH cap, where AH cap is equal to AI cross A perpendicular. There I wrote at the ending. Once again, I will write all of them in the note, students. Okay. Here rho is perpendicular distance from current line to the field point. I will be writing all of them in the note. Okay. So dear students, let us write one note here. H bar in all regions due to K bar ampere per meter surface current density is on infinite area surface is h bar is equal to half into K cross an cap. So this is the formula. If you see here, unit vector, no unit, the unit of K bar is ampere per meter and this is also ampere per meter. So according to Biot-Savart law, h bar direction is perpendicular to the current direction, K bar direction is current direction, and the normal unit vector this one, and cross product. In the Biot-Savart law, you get I dl bar cross A12. dl bar means current direction. A12 is this one unit vector cross operation. So here h bar is generated due to the current. Now here K bar is surface current density. What is An cap here? In the beginning classes, we have studied An cap means normal unit vector to the surface in outward direction. The same definition here also. So here An cap is a normal unit vector to the current surface to the current surface in outward direction, that means away from the current surface, in outward direction and towards the field point. So while learning the formulas, you have to see these type of statements carefully. I will solve one question based on this so that you can understand this. I am writing one question, workbook question. So that question is, plane y is equal to 0 carries a uniform current density k bar is equal to 30 k cap milliampere per meter at 1 comma 20 comma minus 2 what is the magnetic field intensity? What is the magnetic field intensity? So now I am drawing the diagram for your convenience. This is y axis, this is x axis, this is z axis. Y is equal to 0 means xz plane, draw a line parallel to x, draw a line parallel to z. So this is the surface actually. On this k bar, k cap means az cap, that is so k bar is in the z direction actually, like this. This is the current surface. So this is infinity area surface actually, and for this y0 means actually that is x z infinite area surface. Okay, y0 means, so this is xz infinity area surface. Magnetic field is required in front of the surface because in magnetic field location y value is 20. So you want h bar at y is equal to 20. 20 is in front of the surface, so h bar is required here. Now normal unit vector to the surface away from the surface is like this. So 90 degrees. Normal unit vector to this surface, current surface, and away from the surface and towards the field point. The field point is in front of the surface. So this is the AN cap definition. Now compare this in this diagram. So this is actually AY cap. So now, very simple student, where is the field point? Answer, field point is in front of the infinity area surface. Then normal unit vector which makes 90 degrees to this current surface and away from the surface and towards the field point is this direction. Compare this with this in the diagram, that is AY cap. Now here it is given k bar is equal to 30. K cap means here students that is AZ cap actually. So anyway, I cap, J cap, K cap, they are nothing but AX cap, AY cap, AZ cap. Okay. Now H bar formula is equal to half into K bar cross AN cap. So H bar due to the surface current density going on the infinity area surface. This is the formula. So half into K bar is given as 30 into K cap into 10 power minus 3 cross AN cap is AY cap. AY cap is nothing but J cap here. So this is J cap. Now I cap, J cap, K cap. That means AX cap, AY cap, AZ cap. They are in the sequence. Now from this K cap cross J cap, K cross J is equal to minus I. Now that is equal to, this is 15 and this is 10 power minus 3, here minus I into 10 to the power minus 3 ampere per meter, and that is nothing but h bar is equal to minus 15 I cap milliampere per meter. This is the answer. Okay. Now I am writing one more note here. Students, this is h bar due to single infinity area surface. For example, here also one infinity area surface is there, on that k bar is given. Then if you want h bar here, find h bar here due to this infinity area surface, and similarly according to this procedure, find h bar here due to this infinity area surface, then total h bar is sum of them. That is the general procedure. Just I am explaining here, only one surface is there. If two surfaces are there, you find due to each surface and then you add. Okay. Now I am writing one note, that is Ampere's circuital law. Actually here circuital means closed line, actually closed line. Circuit means closed. Ampere's circuital law. I will write the statement, then I will give the mathematical equation also. So Ampere's circuital law states that you see here, closed h dot dl bar, this is ampere per meter multiplied with meter, meter cancel, weight ampere. Ampere means current, the symbol is I. Circle means closed, L means line, closed line. Current inside that closed line, that current inside that closed line, inside the other name is enclosed, current inside the closed line. So this is the mathematical equation of the Ampere circuit law. So this is mathematical equation. How you read this? Ampere circuit law states that the circle means closed, L means line, closed line integral of magnetic field intensity is equal to the I means total current, enclosed means inside this closed line which you have taken. So that is the statement. Physical meaning is, if there is a current in the conductor, then that generates h bar. That h bar is on the closed line. That is the meaning of this. For example, here one conductor is there. In this I current is going. Then how much current is going? I current is going. Then because of this I current, put the thumb in current direction. Then in the closed line direction, h bar is there. So current is, let us say, out of the board, I current here, like this. Then this current generates h bar here in circle direction like this. So on this h bar is there. This is closed line. Actually dot symbol is used for h bar actually. This is a closed line actually. Because h bar lines are, put the thumb in current direction, h bar is circular actually. This is closed line. Circle means closed, L means line. There is a closed line. On that closed line, h bar physical quantity is there. That h bar physical quantity is generated due to the current which is inside this closed line. That is the meaning of that one. So Ampere's circuit law states that the closed line integral of magnetic field, closed line integral of magnetic field intensity is equal to the I means total current, student. Total current enclosed. Enclosed means, what did I say? Inside. So total current enclosed by that closed surface, by that enclosed by that, not surface, enclosed by that closed line, because we are dealing with closed line. So states that the closed line integral of magnetic field intensity is equal to the total current, that is I. Enclosed means inside, total current inside this closed line. That is the statement. Mathematically closed H dot dl bar is equal to I enclosed. So this is the mathematical equation. So this is Ampere circuit law. I will take some examples and I will ask you the question. Okay. Gradually you will understand this. Questions I am writing here. Question 1. There is one line like this. Okay. Now what is closed H dot dl bar on this? It is asked. Then you have to answer that. Okay. Question 2. There is one closed line and inside this dot means out of the board 3 ampere current is there. Now you have to find closed H dot dl for this one. How much? That you have to find. For example, question 3. There is one closed line like this. Now inside this one current conductor is there. For this, what is H bar dot dl bar? Okay. Now there is one closed line here like this, it is given, and here dot cross and dot cross. Here 1 ampere is there, here 2 ampere is there, here minus 3 ampere is there, minus 4 ampere is there. For this, what is H bar dot dl bar? So you have to find them, students. So here there are 4 questions. Now what to do? What is given in the question, first you understand. What is given in the question, first you understand, student. Actually, circle, that means closed. L means line. So that means that this closed line is given here. In the mathematics, if there is a line, definitely there should be a direction. The direction is given here. So what is this actually arrow mark? This arrow mark is closed line direction. That is, they don't give that. You have to understand. One time if you know, then no need to bother. So here this arrow mark is a closed line calculation direction. This arrow mark is closed line calculation direction. This arrow mark is closed line calculation direction. That is one thing over. What is the material of this line? No material. That is imaginary line. That is imaginary line. In Gauss law, no, there was one surface. That surface is imaginary surface. Similarly, here you have to imagine one line here. So that is imaginary line. If there is a conductor inside that line, then on this line H bar physical quantity will be present. H bar physical quantity will be present. If there is no conductor inside this, then H bar generated around this is 0. So on this line, there will be no H bar at all. So anyway, now let us solve these questions. There is one closed line. The direction of closed line is like this. Now inside this closed line, how much current is there? There is no conductor, so current is 0. So answer is 0 to this. Now here, is there any conductor? Yes, that conductor carrying how much current? 3. So you put 3 ampere. Then how to find whether plus or minus? Then for that what you do? Put your thumb, according to right hand thumb rule, put your thumb in current direction, that is out of the board. Then your H bar is a closed finger direction. So because of this current, H bar generated in this direction like this. Now this H bar direction generated due to this current and closed line integral direction both are same. So that is why you take plus. If they are opposite direction, you have to take minus. For example, here, how much current is there? Is there any conductor inside this closed line? Yes. How much current it is carrying? 4 ampere. Now, this current is into the board. So put the thumb into the board, then closed line direction, then in the closed finger direction, H bar is there. So H bar is in this direction, H bar. Now, this H bar generated by this current is opposite to this closed line integral. So that is why minus you have to put. From these two, you understood how to give the sign. The closed line calculation direction and H bar direction generated due to this current are in same direction, you put plus sign. Then closed line integral direction and H bar generated due to this current are opposite direction, then put minus. Then here what to do? You redraw this diagram. Once again you have to draw this diagram by maintaining all positives. Here dot 1 ampere, here cross 2 ampere. If to make it positive, you change the sign of this. Dot is there, put the cross and then take 3 ampere. Here cross is there, change the sign, put the dot and make 4 ampere. Now closed H dot dl bar is equal to, now what you do, inside this closed line 1 ampere also is there, 2 also is there, 3 ampere conductor also is there, 4 ampere conductor also is present. Now you wrote magnitudes of the currents actually. Now what you do, this is out of the board current, then H bar generated due to this is in this direction. Similarly, due to this also H bar generated is in this direction. Now due to this and due to this, into the board, H bar generated is like this, H bar, and due to this also H bar generated due to this also in this direction. Now this H bar direction and closed line direction same, put plus here. This H bar direction and this one opposite, put minus here. This H bar direction and this closed line direction, both this H bar direction, closed line direction opposite, put minus. This H bar direction due to 4 ampere and this closed line direction same, put plus here. So ultimately minus 5 plus 5, so answer is 0 actually, student. So that is the way you decide sign in front of this current. So dear students, if there is a closed line here, then closed line integral of magnetic field intensity, that means total magnetic field intensity, is equal to total current inside. The total current is actually 0 ampere. Even if you see 1 plus 4, 5 ampere out of the board, 2 plus 3, 5 ampere into the board. So this is the way you use that. Now after this, I will solve some questions based on an ampere circuit law. Then after solving them, you have to remember the formulas only. Okay. Now I am solving one question, students. Find the inductance of a coaxial cable between rho is equal to A and B, rho is equal to A and rho is equal to B for H height. So that is the question actually. Already you students know that in coaxial cable, if you recall, and there was a conductor here, this dotted region, and this one is also conductor, outer one. Okay, and this one is z axis, this is radius A, and this one is radius B, rho is equal to B, and of course this one is rho is equal to C. Between A radius and B radius, there is a medium. That medium has epsilon permittivity and mu permeability. Okay, so that is the medium actually here. There is a medium. Now, there is a medium here, students. That may be air medium or otherwise some dielectric medium, any medium it can be. Now, you have to find the inductance of the medium present between the inner and outer conductor for how much height? For h height. Let us take this is z is equal to 0, and automatically this becomes z is equal to h. Overall height is h actually. Okay, that means you are finding the inductance outside this inner conductor, that is also called external inductance to the inner conductor. Anyway, I already told you, once again I am repeating, if you want to find inductance of the medium present between rho is equal to A radius and rho is equal to B radius, then you have to write magnetic field intensity in that medium. So already you know that h bar is equal to I divided by 2 pi rho A pi for A less than rho less than B, and in this actually coaxial cable means here total I current goes, and in outer one down direction I current comes. Now B bar is equal to mu into h bar, so mu into I divided by 2 pi rho A pi. Okay, you know h bar equation between A and B radius. In that medium only you have to find inductance for h height. So B is mu h. Mu is permeability of that medium present between A and B radius. So now magnetic flux crossing the open surface is equal to double integral B bar dot ds bar. Now here B bar is this one, mu into I divided by 2 pi rho A pi dot, what is ds bar in cylindrical system in pi direction? That is d rho dz A pi. Here mu I divided by 2 pi is constant, it came out, A pi dot A pi is 1. So integral d rho by rho, it is given rho varying from A to B, so rho varying from A to B, and integral dz z varying from 0 to h. From this mu I divided by 2 pi, this is ln rho, rho is varying from A to B, and this is z, so z is equal to 0 to h. Now here magnetic flux is equal to mu into I divided by 2 pi ln B minus ln A, that becomes ln B by A. ln means base E, log means base 10. So this is h. Now Here there are no terms actually. N is equal to 1. So inductance is equal to magnetic flux divided by I. So inductance is equal to mu into I cancel. So mu h divided by 2 pi ln B by A Henry. This formula you have to remember. No need to remember this derivation, student. Okay. Now inductance per meter length is L is equal to mu divided by 2 pi ln B by A. So this is Henry per meter length actually. So dear students, already you have seen for coaxial cable, for coaxial cable capacitance between A and B region for H height was, if you recall now, we have derived that actually. That was 2 pi epsilon H divided by ln B by A, that is farad. Then per meter length means H is equal to 1, you have to substitute 2 pi epsilon divided by ln B by A, that is farad per meter. We have derived that. Now this is L. So L into C is equal to L is mu by 2 pi ln B by A, and this is 2 pi epsilon divided by ln B by A. So ultimately 2 pi cancel, and then ln B by A cancel, and mu epsilon remains. So L into C is equal to mu into epsilon. Actually this inductance, no dear students, this inductance is external to the inner conductor. So it is also called as L external. This inductance is also called as L external. That means that inductance is external to the inner conductor. So this is the inner conductor. Now the medium present here is external to this conductor. So that is why it is called external inductance. Okay. Simple thing. In whichever region you want to find inductance, in the derivation you have to use magnetic field equation of that region. जिस रीजन का इंडक्टेंस फाइंड करना है आप लोग, वो डेरिवेशन में उस रीजन का मैग्नेटिक फील्ड इक्वेशन यूज करना है. ठीक है. सो एनीवे L into C is equal to mu epsilon. Okay. You can see that this mu and epsilon, they are the parameters of the medium present between the inner and outer conductors. That is why you have to take inductance as well as capacitance for the medium present between the inner and outer conductors of the coaxial cable. So now we are going to derive for other cases. Inductance we will derive for other cases. So dear students, now let us discuss boundary conditions. For example, here there is one surface like this. This is surface. From front you see, from front side you see it looks like a line, but actually this is a surface. So let us say this is z is equal to 0 surface, or otherwise xy plane. Then this is z greater than 0, this is z less than 0. Okay. Now here this is medium 1, this is medium 1, simply it is called m1. This is medium 2, this is medium 2, simply it is called medium 2, m2. This has parameters like mu1, epsilon 1, sigma 1. This has parameters like mu 2, epsilon 2, sigma 2, like that parameters are there. Now here fields are E1 bar, D1 bar, H1 bar, B1 bar. Similarly here fields are in second medium U2 bar and D2 bar and H2 bar and B2 bar, like that. So I will tell you one simple example. For example, this is wood material. Lakadi hai ye. Here, what I am doing, I will take this as a y-axis, this as a z-axis. Out of the body is x-axis. Now here, this is x, xy plane is there. So xy plane, or otherwise z is equal to 0 plane, z is equal to 0 plane, or otherwise xy plane is there here, xy plane. Okay, this one. So this plane is like this now. It is a surface xy plane, but from front it looks like a line. Now here I am putting one charge source here that generates electric field vector E bar. Then this medium has epsilon, then D bar is equal to epsilon E bar. Now this electric field was going like this. Now whenever this electric field goes like this in air medium, this is air medium. Now suddenly, for example, wood material came here. So now this electric field enters into wood material, that is called medium 2. The wood material has different parameters. Now wherever medium 1, that is air medium, and wherever medium 2, that means wood material, are separated, there you have to imagine one surface. There you have to imagine one surface. This is called imaginary surface. This imaginary surface is called as boundary surface. This imaginary surface separates air medium, that is called medium 1, and wood medium, that is called medium 2. So boundary is a imaginary surface whose thickness tends to 0 and it separates medium 1 and medium 2. So that is boundary. Now here wood material is there. Wherever wood material starts, that is taken as 0, z is equal to 0 height. For example, this is all wood material, then that is called as z is greater than 0. Here medium 2 is there. For example, that is wood medium, wood material. And below this, whatever medium is there below this, that is called as medium 1. That is, for example, here air material. Now they are called as, here some source is there, charge source, that generates these fields. In medium 1 is called as E1, so suffix 1 for medium 1. Now the question is, if this field enters into the wood medium, then what is the electric field there and what is the D2 there? We have to find. So now the question is, given electric field equation in medium 1, and then what is electric field equation in medium 2? So these fields in medium 2 can be calculated when fields in medium 1 are given by using the boundary conditions. Now boundary conditions means the relations between fields of medium 1 and fields of medium 2, that is called boundary conditions. Boundary conditions means relation between fields of medium 1 and medium 2. We have to see what are those boundary conditions. Now here, for example, here one imaginary surface is there. This imaginary surface separates medium 2, that is wood material, and air material. Now this diagram can be drawn like this also. So now this is z is equal to 0. Here it is drawn, z is equal to 0. This side air medium, for example, z less than 0. This side wood medium, for example, it is z greater than 0. So in examination, whether boundary surface is given like this or like this, it doesn't matter. The name of this boundary matters. It can be x is equal to 0 boundary, any boundary. Now, for example, students, E1 bar is equal to 3ax plus 4ay 10az is given, for example. Now here with this is which axis? Z axis. For z is equal to 0 boundary, z component is normal component, because z component means that is like this. 10az means it is like this. So this makes how much angle with this surface? 90 degrees. That means 10az is called a normal component. So this electric field normal component in medium 1, and then this boundary is this surface, boundary surface or otherwise boundary, both are same. बाउंड्री मीन्स बाउंड्री सरफेस. अगर आपके पास पेशेंस है तो बाउंड्री सरफेस बोलिए, पेशेंस नहीं है तो बाउंड्री बोलिए. Boundary or otherwise boundary surface separates medium 1 and medium 2. For example, in this case, this boundary is x and y. So this boundary is parallel to xy plane. Now x component is in x direction, that is also parallel. Y component is in y direction, that is also parallel. So in name itself it is there. For xy plane or otherwise xy boundary, this x comma y components are parallel. Other name of parallel is tangential. So this is electric field tangential component. So now the conclusion is any vector E bar can be written as tangential component and a normal component. So any vector E bar has tangential component, normal component. Now how to find normal component and tangential component? In the examination, if z is equal to 0 boundary is given, then z component is normal component, others are tangential components. In examination, if x is equal to 0 boundary is given, x component is normal component, others are tangential. In examination, if y is equal to 0 boundary is given, y component is normal component, then x and z are tangential components. In that way you have to find. And also, dear students, any complicated surface is given, boundary surface, that boundary surface is like this or like this is there, then what they do, uh, they give the surface function. So if you know surface function x y z, then normal unit vector is grad f divided by modulus of grad f. Okay, now if you want E n1 bar, then you take electric field vector in medium 1, take the dot product with an cap, then dot product gives scalar, that gives magnitude of en1 bar, then again multiply with an cap, then you get vector called en1 bar vector, you get normal component. Now here you have seen en1 plus et1 is equal to e1 bar. So from this e t1 bar is equal to e1 bar minus en1 bar, so that you get the et1 bar. So this is the general procedure to find the, what do you say, tangential and normal component. For example, this procedure I will apply for this case. For this case, it is very simple case. Here the boundary function is surface function is fx comma y comma z is equal to 0 is the equation on this boundary surface. So that is z minus 0. Now gradient of f is equal to dou f by dou x 0, dou f by dou y 0, dou f by dou z 1, dou f by dou z into az 1 az grad f. Now an cap is equal to grad f divided by modulus of grad f, that is nothing but az cap divided by modulus of this one is 1 actually, so that is az. Now what you do, en1 means given vector is this one, that is 3ax plus 4ay plus 10az dot an is nothing but here az, and of again az you have to write. So ultimately this is equal to az dot x 0, az dot ay 0, az dot az is 10, 10 of az, 10 az you get. So this is the en1 bar. Now et1 bar is equal to e1 bar is 3ax plus 4ay plus 10az minus of en1 means 10az. So this cancel, you get this one. So for simple cases, directly we will write if any complicated surface comes, this is the way you find normal and tangential components. So dear students, in this way you have a tangential and normal component for every vector. So let us write until this. Now whatever I have explained, let us write here. Here this E1 bar, that means electric field in medium 1, is generated due to some source here, maybe some charge source, line source, like that, some charge source, point charge source, line charge source, like that. So these fields are generated in the medium 1 due to some source. Then these fields will be going like this. Then suddenly here medium 2 comes. Then the equations in medium 2 are going to change actually, right? Now what I was explaining, any vector has a tangential component and normal component. Similarly this one also, dt1 bar dn1 bar. So this is a ht1 bar plus hn1 bar. This is equal to bt1 bar plus bn1 bar. Similarly this is a et2 bar plus en2 bar. This is dt2 plus dn2 bar. This is ht2 plus hn2 bar. This is tangential component plus normal component, but for medium 2 you have to put suffix 2 here. Now here this is the boundary surface, then normal unit vector, that means which makes 90 degrees to this boundary surface, normal unit vector from medium 1 to medium 2 is a cap means a unit vector, n means normal from medium 1 to medium 2. So this is medium 1 and this is medium 2. How much angle it makes? 90 degrees. So what is the equation of this? Grad f divided by modulus of grad f, where f is surface function, this boundary surface function actually. So here I am writing a note that for z is equal to 0 boundary, for z is equal to 0 boundary surface, that means that is xy surface. For z is equal to 0 boundary surface, z component is normal, comma x comma y components are tangential. Tangential means parallel. Okay, tangential. Example, given E1 bar is equal to minus 3ax plus 4ay plus 6az, then for z is equal to 0 boundary surface, z component is normal component. So En1 bar is equal to 6az. Now remaining components are tangential components. Et1 is equal to minus 3ax plus 4ay. So this is one point you have to remember. Okay, students. If x comes here and x equal to 0, then x component is normal component. Remaining are the tangential components. Next, we have to write that note also for general boundary, that is general discussion. Okay, second point in the note. If f x comma y comma z is the surface function, then an12 is equal to grad f divided by modulus of grad f. Here an12 is nothing but an12 is normal unit vector to the boundary surface from medium 1 to medium 2. Now En1 bar is equal to E1 bar dot An12 of An12. Okay. Now E1 bar is equal to Et1 bar plus En1 bar. From this, Et1 bar is equal to E1 bar minus En1 bar. So this is the way. If E1 bar is given, then you can find En1 bar. Then from that E1 bar minus En1 bar gives Et1 bar. So this is the way. If any complicated surface is there, then this is the procedure to find the tangential and normal components. Okay. So these 2 points you have to remember, students. They are in the note. Now I will do some rough work. So no need to bother about this rough work actually. Just to get the clarity on the equations of the boundary surface, we are going to do the rough work here. After that, we will write the boundary conditions. Okay, students. So here, let us take one boundary surface. Then boundary surface means what, students? I will write some points here. I will write some points. This is the note here. First point. Boundary is a surface whose thickness T tends to 0. Next, boundary surface separates medium 1 and medium 2. Okay. Next, boundary conditions, or otherwise I will do like this. If fields of one medium, are given, then using boundary conditions, we can find fields of other medium. That is the use of the boundary conditions. Now I will do rough work here. There are 4 Maxwell equations till now we have discussed. E dot dl is equal to 0 and double d bar dot ds bar is equal to q and closed h dot dl is equal to I double integral b bar dot ds bar is equal to 0. To calculate this one, we need closed line. To calculate this one also we need closed line. To calculate both of them we need closed surface. For example, here I will consider one boundary surface. This is the surface. The thickness of that tends to 0. So I am taking here boundary surface. This is medium 1 and this is medium 2. Now in medium 1, E1 bar is there, that is equal to ET1 plus EN1. Similarly in medium 2, E2 bar is there, that is ET2 plus EN2, like this it is. Okay. Now I want to derive this near the boundary. So to do this derivation, I have to take closed line near the boundary. So I will take the closed line. That closed line thickness tends to 0. So here there is a boundary surface whose thickness tends to 0. I am doing a derivation near the boundary. So for that derivation, I have to take a closed line, first line, second line, third line, and here fourth line. So like this, I am doing the derivation, line integral I am doing. So if you are doing line integral, you have to take the direction here. Let us take this is delta L or otherwise DL. This is also delta L. Of course, down direction means minus delta L you have to take. If you take this plus delta L, this is minus delta L. Now I am taking this is delta T, but according to boundary definition, this thickness of the boundary tends to 0. So I am taking the closed line near the boundary in such a way this closed line touches medium 1 and medium 2, but delta T tends to 0 actually. So this is delta T by 2 this side also delta T by 2, but anyway that delta T is equal to 0. Now students, what is the meaning of tangential? If you see carefully here, tangential component means which is parallel to this one. Any component parallel to this boundary is called tangential. So along this line, ET1 bar will be there, ET1 bar, because ET1 bar is parallel to this one. Similarly here, ET2 bar will be there parallel to this line, ET2 bar will be there. But in this direction, like this, no, normal component will be there, normal component. So En1 bar is 90 degrees to this boundary. Similarly here En2 bar is there. Now if I calculate the closed E dot dl here, now this closed line has 4 lines, first line, second line, third line, fourth line. For first line, this E bar is ET1 bar. Dot dl bar is nothing but delta L. Do you think you have to take the integral? No need, because this is already small length. No need to take integral. Now plus here na this like this normal component is En1 bar. En1 bar dot delta L here is for this one delta T divided by 2, but according to the definition for a boundary delta T tends to 0, so this becomes 0, so no need to take this one. That means no need to take normal components here, only tangential components you have to take. Now this one, if you take for line 3 ET1 here, and this side it is ET2 dot, if you take this as a delta L, then downside it is this one, that is minus delta L. So minus delta L. Now no need to calculate for this because thickness tends to 0. This is equal to 0. Now you send this side ET1 dot delta L plus is equal to minus is there no, so ET2 dot delta L. When this comes this side, minus gone. Now compare both sides. If you compare both sides, then you get ET1 bar is equal to ET2 bar. So even if you take modulus also, that is equal. So how you read this one? Tangential components of electric field intensity in medium 1 is equal to tangential component of electric field intensity in medium 2. So in mathematics subject, actually, in the zero thickness, that means the boundary thickness is zero. In the zero thickness, if this side components are same, then you call them as continuous. So continuous means uh, this side electric field component, tangential component, this side component, both are equal, then you call them as a continuous. Continuous means equal, actually. So how you read this in other way? Tangential components of electric field intensities are continuous. Continuous means equal. Continuous at the boundary surface. So this derivation you should not learn. Even if you learn this derivation, there is no use. आप लोग ये डेरिवेशन सीखेंगे, कोई फायदा नहीं है आपको. But how you use this in solving questions, that is important. Anyway, I am doing rough work here. So now let us later on we will write the boundary conditions. So dear students, similarly if I write the h1 bar here, so h1 bar is equal to ht1 plus hn1, like this in medium 1, and in medium 2 if I write h2 bar is equal to ht2 plus hn2, so like this. Now here because I am going to take this equation here, so for that I have to take a closed line once again, like this. If I take a closed line, so like this is the first one, second one, third one, fourth one. Once again delta t, same thing. Delta t, thickness of this delta t tends to 0. That means this thickness this thickness tends to 0 because we are doing derivation near the boundary, actually. Now in this direction ht1 bar is there, in this direction ht2 bar is there. That means this ht1 bar is tangential or otherwise parallel to this boundary surface, and hn1 is normal to this, that means 90 degrees to boundary surface. No need to take normal components because delta t is becoming 0 here. Now closed h dot dl is equal to I. Now if you write this one similar to this, same ht1 dot delta L on this line 1. For line 2, because delta t tends to 0, it becomes 0. So plus h t2 for this one. But you take this as a delta L bar. So upwards, then downwards is minus delta L bar. So dot minus delta L bar, that is equal to. Now what is this one? If you see carefully, actually on the surface like this, surface current density will be present. Already you know that surface current density is k bar. Now here k bar dot here you get current is equal to k bar and this is like you say here k bar current is equal to k bar. This delta actually here how to show, dear students, k bar is defined as current by cross sectional width. Current by cross sectional width, actually. So for example here k bar direction can be in two ways, student. So k bar can be like this also. If it is like this, then delta L becomes the cross sectional width. So the unit of this is ampere per meter, and if I take delta L here, again meter. So meter cancel, dear students. If meter cancel, then ultimately you get current here. Anyway, just I want to tell you here that HT1 bar minus, here minus is there, minus HT2 bar depends on surface current density. But actually this is not the correct way, because K bar cross AN12 you take, then you get the magnetic field direction. So anyway, uh, if I do like this, na, HT1 bar magnitude and HT2 bar magnitude if I take, then I will get here magnitude of the surface current density like this, but it is in scalar form. In vector form, if you do the derivation for generalized case, you get like this: HT1 bar minus HT2 bar is equal to AN12 cross K bar. So did you remember, students? If there is a K bar surface current density, then you take cross product with normal unit vector, then you get the magnetic field generated. That magnetic field generated should be equated to the difference of magnetic field intensities here. So that is the derivation for that. This equation you have to remember, dear students. I will write that later on. Anyway, if surface current density is 0 here, then if it is 0, then what will happen? Then both HT1 bar is equal to HT2 bar it becomes. Then in that case, they are continuous. That means HT1 bar HT2 is equal, HT1 bar is equal to HT2, then only they are then they are continuous if K bar is equal to 0. If K bar is there, then these tangential components are not equal. They are called discontinuous. Discontinuous means not equal. Similar to this, if you take this equation, this one near the boundary, so D1 bar is equal to DT1 and DN1, and this is medium 1. Similarly here in second medium 2, D2 bar is equal to DT2 plus DN2. Now here, if you are talking of normal components, uh, this tangential component is parallel to this boundary, then normal component is 90 degrees to this boundary, like this. Similarly here also DN2 is there, and parallel to this boundary dt2 is there. Now you are going to do this derivation here, that d bar dot ds bar is equal to q. So to derive this, you have to take the closed surface. Closed surface I will take here cylinder, for example, like this cylinder I will take. Now this closed surface, this is one surface, this circular surface. This is also one surface. But the cylinder has side surface. But according to the definition, delta T tends to 0. So this cylinder looks like this, and delta T tends to 0, and like this it looks like. Very closer it is. So delta T tends to 0, then cylindrical surface becomes negligible. Only this side surface and this side surface will be there. But here the surface vector for this is normal to this surface and away from this surface. The surface vector for this side is normal to this surface and away from this, like this delta S bar, like this. Now if I do this side here, d bar is d n1 bar. If I take this as a plus delta S, then plus for this side I am doing. For side surface, it is 0 because thickness tends to 0. So area of that is 0. Next. So students, the side surface area is 2 pi rho h for cylinder, but I am taking height of this as delta t. Delta t tends to 0 means that is negligible. So no need to take that one. Now here dn2 is like this dot. If I take this as a plus delta s, then opposite of that is I will take minus delta s, like this. So this is equal to, on the boundary surface, rho s will be there, surface current density, surface charge density, rho s will be there. So rho s into delta s you have to take, because on delta s surface, how much charge is there? So delta s into rho s. Now I can write this one like this. If you take a dot product na, I will write like this. Delta s can be written as delta s bar can be written as delta s into normal unit vector and dn1 bar plus minus I will get this side, minus I will get this side. So this is nothing but dn2 bar. I will do one thing, student. dn1 bar can be written as modulus of dn1 bar multiplied with delta s bar. So delta s bar. Okay. Now dn1 bar an cap, because dn1 bar can be written as magnitude and direction. Direction is normal. Now here also dn2 bar can be written as modulus of that dn2 bar into an cap unit vector dot minus I wrote here, delta s bar can be written as delta s into an cap, that is equal to rho s into delta s. Here no need to take bar, because q is the charge, charge is scalar, rho s is scalar, scalar multiplied with scalar gives scalar. Here delta s, that means magnitude is taken. Now an dot an is 1 actually, so dn1 into del s minus modulus of dn2 an dot an is 1 into del s is equal to rho s into del s. This del s cancel, so you get dn1 modulus dn2 modulus is equal to rho s. This is correct actually, student. This is scalar and magnitude is scalar, magnitude is scalar. This is coulomb per meter square. This is also coulomb per meter square. This is also coulomb per meter square. What this equation tells, if dn1 is coming like this, then if there is a rho s on this surface, actually dn1 is coming like this because of some charge source here. Then when it comes to medium 2, on the way there was a surface, on that surface charge was there. Because of that also some d bar is produced. So now that d bar, because of that also d bar is produced, then that extra d bar will be there. So that is this one. That means here dn2 bar is there, let us say. Now here dn2 bar is there, let us say. This dn2 bar is equal to what this says, incoming is dn1 bar, outgoing is dn2 bar. This outgoing field, that is dn2 bar, outgoing field, that is dn2 bar, I am separating this. Outgoing field from the boundary, that is dn2 bar, is equal to incoming field, that is dn1 bar, plus rho s effect. That's what you get. So here in the scalar form, if you write, it is like this. And there are two cases. In one case, you get dn2 minus dn1 is equal to rho s. In other case, you get dn1 minus dn2 is equal to rho s. I will make separate diagrams in the note. I will write them. Now you don't bother about this one. Now ultimately here, students, the equation can be dn1 minus dn2 is equal to rho s. Otherwise, second equation is dn2 minus dn1 is equal to rho s. First equation comes for one case, second equation comes for second case. Now I will not explain. In the note I will write, I will explain there itself. Now we will not waste our time. So in this way, dear students, if there is a rho s, that means surface charge density is there on the boundary, then dn1 and dn2, they are not equal. They are not equal because of this surface charge density. So if they are not equal means you call them as discontinuous. So how you read this one? Normal components of electric flux densities are discontinuous. Discontinuous means not equal on the boundary surface due to surface charge density present. If it is a charge-free boundary means rho s 0. So if rho s 0, then again dn1 is equal to dn2. So then you say they are continuous. Continuous means equal. So mod. In mod form also they are equal. In the vector form also they are equal, students. Okay. Now similar to this, you do the derivation, na? This double integral b bar dot ds bar 0. Similar to this, if you do the derivation, then here you get bn1 bar, here you get bn2 bar, then both will be equal like this. Then in mod form also they are equal. Now, dear students, there is no need to learn these derivations. It is not useful. Even if you learn, it means that you are wasting your time. Just to get the feeling, I told you why I took some time to explain them. I wanted you to understand one simple thing. That is why I explained. Otherwise, there is no use of them. It is 100% not useful. Then, what is there to observe here? That point is, boundary conditions means we get tangential relations for intensities. This one. This is magnetic field intensity. This is electric field intensity. For intensities, we get tangential relation. That is one point. For densities, this is also density, electric flux density. This is also density, magnetic flux density. For densities, we get normal relations. That point is to be remembered from these things. So these are not at all useful, students. So what did you observe? Boundary conditions means we get tangential relations for intensities and normal relations for densities. So how many boundary conditions are there? 4. For intensities, 2 relations. For densities, 2 relations. On the boundary surface, what sources can be there? I explained you point charge, line charge, surface charge, and volume charge. Among them, Coulomb per meter square surface charge density is present on the boundary surface. That is why here in this rho s comes actually. Coming to the current sources, line current, surface current density, volume current density. This surface current density unit is ampere per meter. It presents on the surface. That only comes in the h bar derivation. So now this discussion not useful to you, and now what is useful we will write there. So dear students, until this, what to remember? This is one point, this is second point. Only these two things you have to remember. After this, I will write 4 points. Those things you have to remember. Okay. This is not useful to write also. Now I will be writing the boundary conditions. How many boundary conditions are there, dear students? Total there are 4 boundary conditions. For intensities, 2 boundary conditions. For densities, 2 boundary conditions. Okay. So here I am writing the boundary conditions. Here, note, there are 4 boundary conditions. First one statement is the tangential components of electric field intensities. The tangential components of electric field intensities are continuous. Continuous means equal, students. Continuous means equal. Continuous at the boundary surface. This is the statement. The tangential components of electric field intensities are continuous, that means equal at the boundary surface. So, mathematically, ET1 bar is equal to ET2 bar. So, in magnitude form also, they are equal, students. In vector form also they are equal, magnitude form also they are equal. Okay. Now, second one, the normal components of electric flux densities, electric flux densities are discontinuous. Discontinuous means unequal. The normal components of electric flux densities are discontinuous at the boundary surface by an amount equal to the surface charge density present on the boundary surface. Mathematically, there are two cases. Case 1, in the diagram, this is medium 1, this is medium 2. In the examination, for example, in the diagram, if they give dn1 is like this, arrow mark is given like this, and similarly dn2 is like this, then rho s is present here. Then in this case, equation is outgoing from the boundary. Outgoing is this one. Outgoing from the boundary minus incoming towards the boundary is equal to how much surface charge density present on the boundary surface. This is the one. This also can be written like this, student. D2 bar minus D1 bar dot product with AN12, that is normal unit vector, gives rho s. So this equation, this one. So what is happening here? D2 bar has a tangential component and normal component, but if you take dot product with normal unit vector, then dot product gives scalar. Scalar means magnitude. So you get magnitude of the normal component you get. Similarly, D1 bar has a tangential and normal component. If you take dot product with normal, then tangential component becomes 0 and the normal component magnitude you get, because dot product gives magnitude. So this one modulus. What I am telling you is that, so D2 bar minus D1 bar dot AN12 is equal to rho s. I am telling this D2 bar is nothing but this D2 bar has D T2 plus dN2 bar minus of this one has dt1 plus dn1 bar dot product with an12 is equal to rho s, like this, no? Like this. Now this d22 can be written as dt2 modulus A A T bar, that means tangential unit vector, plus this can be written as modulus of dn2 and an12 normal unit vector. This you can write like this. Okay, this one written like this one written like this. Similarly, this one also dot an12. No, I will explain for one thing. So this an12 for this. Okay, this an12 dot at tangential and normal 90 degrees. No, so dot product becomes 0. So this becomes 0. Now an12 dot an12 is 1. So what remains is modulus of dn2. Similarly, here also remains modulus of dn1, and that is equal to rho s is there. So anyway, here what equation you have to remember is that I am putting this in the box, students. So this equation you have to remember here, this one. So for example, this 3 is given, it is 5 is given, then you want a dn2 bar. So dn2 bar is equal to, this is 3 and this is magnitude is 5. You send this side, total dn2 bar becomes magnitude is 8. Then if you want modulus of dn2 bar is equal to 8, you got then dn2 bar is equal to simply 8 into an12 bar normal unit vector. How you get this normal unit vector an12 bar? I told you earlier procedure also to get an12 bar. So this is the an12 bar equation, right? Okay. For example, for z is equal to 0 boundary, an12 bar is az cap, like that. Okay. So this is a one thing equation which you have to see. If you want, you can write this, or otherwise you remove that one, students, because here na only this is the case. This is medium 1, this is medium 2. How do you know this field is coming like this? Because here some source will be there. From that source this is coming. That direction will be given in examination. वो एग्जाम में दे देता है, फील्ड से ऐसा आएगा, ऐसा जाएगा, कैसे जाएगा, वो एग्जाम में दे देता है आपको. आप परेशान होने की जरूरत नहीं है. फॉर एग्जाम्पल case 2, students, case 2, in this is medium 1 and this is medium 2, and they have given dn2 coming like this and dn1 going like this. Then here rho s is given. In this case also, outgoing from the boundary minus incoming towards the boundary is equal to how much surface charge density present on the boundary. This is the equation. So depends on the situation, you have to take this one. These directions are given in the examination. For example, here here charge source is there. This charge source generates this one. It goes like this in medium 2, then it enters into medium 1, like that. So if rho s 0, that means charge free boundary. Questions in question they give charge free boundary means rho s 0. Then in that case, modulus of dn1, modulus of dn2, both are equal. So that implies in vector form also they are equal, student. dn1, dn2, they are equal. Then third boundary condition, the tangential components, of magnetic field intensities, the tangential components of magnetic field intensities are discontinuous. That means unequal. Discontinuous means unequal, discontinuous at the boundary surface by an amount equal to the surface current density, surface current density, that means k bar, that is present on the surface. Surface means boundary surface. So this one mathematically you get like this: ht1 bar minus ht2 bar. I did not do the complete derivation for this. Okay, so that is equal to an12 cross k bar, because no need to do the derivations, I told you. I will give one hint here. The unit of this is ampere per meter, no unit. So overall unit is ampere per meter. This is also ampere per meter, this is also ampere per meter. Here also the unit of this is coulomb per meter square. This is coulomb per meter square, coulomb per meter square. This is scalar, so that is why this side also they are in modulus form. But here this is vector, so this overall is vector, and this is also in vector form, this is also in vector form, students. Now here an12 bar I wrote at the beginning. You have to remember that normal unit vector to the boundary surface from medium 1 to medium 2, that is. So that is nothing but grad f by modulus of grad f. So in some books they write like this also, then that is also correct. ht1 bar minus ht2 bar cross an12 bar is equal to k bar. This is also correct. You can write like this also: h1 bar minus h2 bar cross an12 is equal to k bar. This is also correct, students, because here h1 bar is equal to ht1 ht1 into at1, that means tangential unit vector, plus h n1 and an12, you can write 1 2. Now minus of something is there. First you take cross product this to this one. Actually the meaning of this is h1 cross an12 minus h2 cross an12. First I am doing for this. So this is h1 bar, I am doing cross an12. Then on at cross an, that only remains an cross an becomes 0. For example, this is ay, this is ay, ay cross ay becomes 0. So this term is gone. Only ht1 of at1 cross an1, this only remains. That's what I want to tell students. So an cross an becomes 0. If an cross an becomes 0, then what is remaining? an12 cross tangential component, an12 cross tangential component only remains. That is why in the books they write like this also. Doesn't matter. But why I kept this in the box, no, students? This is useful in solving the questions. This is ready-made equation. For example, you know this one ht1. ht1 is known. Then ht1 is known. You send this side, then you can find ht2. So if ht2 is known, you send this side, then ht1 you can find. So this equation is useful to you for examination. So if k bar is 0, then what happens? If k bar is 0, that is called current free boundary. Current free boundary. Then ht1 bar is equal to ht2 bar. They are again continuous actually. Next, last boundary condition, the normal components, the normal components of magnetic flux densities, normal flux densities, the normal components of magnetic flux densities are continuous, that means equal, continuous at the boundary surface. That is mathematically Bn1 bar is equal to Bn2 bar. So students, actually B is equal to mu into H N1. So B is equal to mu into H N2. So this is for second medium. This is for first medium. Like this you can write. But I am not writing these things. This already you know. You should not learn all the equations. It is not useful. This is the main equation you learn. If you know this, then if you want in terms of H, then Bn1 is equal to mu1 into Hn1. That already you know. B is equal to mu H. So that is the relation actually. So dear students, here what you have to, till now we have discussed so many things. Now I am telling you what to read. You see, you read this one. Actually, this one you read. Okay, first point, second point. This is first point, and this is second point. Then after that, this one, and this one, and this one you read. Now other than this, whatever discussed, you forget that one. This much is more than enough. So those 2 points, these 4 points, and finally one more statement is there for conductor and some dielectric boundary. That one you have to remember. Overall, these 4 points, the 2 points, and one more point is there. I will write that. That one you have to remember. Then all the boundary conditions will be over, students. Boundary condition. This is important topic actually. So these are called 4 general boundary conditions. General means what is the meaning? General means here medium 1 can be air medium, and this is dielectric medium. This is dielectric. It can be air. It can be a conductor. It can be air. It can be a conductor. It can be a dielectric. It is magnetic material. It is air material. So for any case, these equations are valid. That is why they are called general boundary conditions. Now one special case is there. We will discuss that special case. What is that special case? One side actually dielectric medium is there. Other side conductor medium is there. I am telling you, don't do derivations. If you want to be in top 10, you have to listen whatever faculty says. Because if you are doing all derivations and learning, there is no use. You are wasting your time, you are wasting your energy. You are not studying what is required for examination. So dear students, actually for examination, if you want to get into top 10, simply you learn the formula and then remember that formula, then understand how you use that formula, in solving the question, then automatically you will be in top 10. Because learning all the derivations, no students, in no way they are useful. कोई फायदा नहीं है. बट मैं तो डेरिवेशंस करते रहता हूँ, क्योंकि आप फार्मूलास आसान से याद होने के लिए मैं डेरिवेशंस करता हूँ. क्योंकि बिना डेरिवेशन को आपको फार्मूला बताएंगे, थोड़ा दिमाग एक्सेप्ट नहीं करता है. थोड़ा डेरिवेशन करेंगे ना, वो दिमाग कुछ देखते रहता है, कुछ हो रहा है करके. कुछ होने के बाद, मतलब डेरिवेशन कंप्लीट होने के बाद, वो फार्मूला अपने आप याद हो जाता है. फिर आप लोग वो फार्मूला को क्वेश्चन सॉल्व करने में यूज करेंगे, वो बढ़िया से याद हो जाता है फार्मूला. सो इधर एक छोटा डेरिवेशन कर रहा हूँ, फिर वो डेरिवेशन सीखना नहीं है आप लोग, उसके बाद जो रिजल्ट आएगा वो देखना है. सो आई एम राइटिंग हियर ऑब्जर्वेशन. ऑब्जर्वेशन मतलब ऑब्जर्व करो, ऑब्जर्व करने के बाद एक इंपॉर्टेंट पॉइंट आएगा, उसको नोट में लिखूंगा, वो याद रखो, वो है ऑब्जर्व करना बस. इसको बाद में नहीं पढ़ना है. नाउ इधर z लेस देन 0 और ये z इज इक्वल टू 0 बाउंड्री है, ये z ग्रेटर देन 0, ये मीडियम 2 है, ये मीडियम 1 है. फॉर एग्जाम्पल ये डाइइलेक्ट्रिक मान लीजिए, इधर से इधर ऐसा बहुत बड़ा कंडक्टर है, ये मीडियम 2, ये पूरा कंडक्टर है ऐसा. ये क्या है, ये कंडक्टर मीडियम है. कंडक्टर में सिग्मा जो है वो इन्फिनिटी रहता है, ये सेकंड मीडियम है इसलिए मैं सिग्मा 2 लिखा है इधर. और कंडक्टर में J इज इक्वल टू सिग्मा ये होता है और E इज इक्वल टू J बाई सिग्मा होता है, ये सेकंड मीडियम है इसलिए सफिक्स 2 लिखना है. और थोड़ा बढ़ा देता हूँ. अभी इसमें J2 बाई ये ऑलमोस्ट इन्फिनिटी है, इसका मतलब 0 आया. सो इलेक्ट्रिक फील्ड इन मीडियम 2 0 आया ना, इलेक्ट्रिक फील्ड इन मीडियम 2 0 आया. इसका मतलब मीडियम 2 में इलेक्ट्रिक फील्ड हैज टेंजेंशियल कंपोनेंट एंड नॉर्मल कंपोनेंट 0 है, क्योंकि E2 है, इट इज ए सम ऑफ टेंजेंशियल एंड नॉर्मल कंपोनेंट्स. ओके. नाउ if vector itself not there, vector खुद गायब हो गया, vector itself is not there, from that vector whatever components you get they also become 0. वेक्टर खुद गायब हो गया, वेक्टर से निकलने वाला जो टेंजेंशियल नॉर्मल कंपोनेंट्स है वो भी नहीं रहेगा. इसका मतलब है Et2 0 एंड En2 0 है, क्योंकि वेक्टर खुद गायब है, वेक्टर है ही नहीं है. कंक्लूजन क्या है स्टूडेंट इसमें? इन वेरी गुड कंडक्टर conductivity is infinity, resistance is 0, resistance 0 means voltage drop is 0, electric field means voltage divided by distance. If voltage 0, electric field also 0. Then if total electric field is 0, then electric field generates magnetic field, then total magnetic field is also 0 inside the good conductor. So conclusion is, inside the good conductor it is medium 2. Actually this is very big piece of conductor here like this, and outside this medium 1 is there, that is dielectric. Actually outside this conductor medium 1 is there, this is conductor surface actually. Okay. Now inside the conductor student, electric field is 0, total electric field. Magnetic field is also 0 because electric field generates magnetic field. Now if electric field component is 0, tangential electric field, normal electric field 0. Similarly total magnetic field is also 0 because electric field generates magnetic field. Then magnetic field, tangential, normal components are also 0. This information is required in solving question, student. So this is special case, this is a dielectric and conductor boundary it is. Okay. Now in the medium 2 we have discussed. Now what is the first boundary condition? The first boundary condition is Et1 bar is equal to Et2 bar. This is general boundary condition, student. I will do one thing. I will take this as equation 1, this as equation 2, this as equation 3. This is general boundary condition. Now substitute equation 1 in 3, then you get Et1 bar is equal to 0. That means this is conductor. In this, inside this conductor, tangential component is also 0, normal component is 0. Then outside this conductor, this is the surface, and in the medium 1, tangential component is again 0, it has become. Tangential component means the component which is parallel to the surface in medium 1 side, that has also become 0. Now I will put this in the box later on. ये डब्बा में रखूंगा, note में लिखूंगा मैं. I will write in the note. So now students, what is the second general boundary condition? So general boundary condition, general means applicable for all the cases, is dn1 minus dn2 is equal to rho s. Now if I write this in terms of electric field, this is epsilon 2 en2. Let us say equation 5. Now en2 is 0, substitute this here. So you put equation 2 in 5, that means dn1 is there, and this becomes 0, that is equal to rho s. So dn1 is equal to rho s came now. If you want, you can write this is epsilon 1 en1 is equal to rho s, you can write. So en1 is equal to rho s by epsilon 1, like this. So these are the results, students. I will write these results in the note. You should not study this one. Now here you got I am going to write note here. You see here, students, I will write note here. It is little clean here. Note, I am writing here, between dielectric, that is medium 1, student, and conductor is medium 2 here. Boundary, I am drawing diagram here. This is medium 2, that is conductor, okay, and this is medium 1, that is dielectric. So this side electric field is 0, and of course tangential component of electric field also 0, normal component is 0. So now this side tangential component in medium 1 is also 0, but normal component is not 0. Students, here two components are there, tangential, normal. Here also two components, tangential, normal. So total three components are 0 here. Only electric field normal D is equal to epsilon E. So dn1 is equal to epsilon 1 into en1. So mod only normal component is present here, but others are not there. So that means what did I write here? Modulus of en1 is equal to rho s by epsilon 1. So what is this rho s, student? Now I will explain the meaning of this. For example, on this conductor surface, rho s is there, then that rho s, for example, positive rho s is there, positive rho s plus positive rho s is there. Then we have studied because of this rho s, electric flux lines, electric field intensity lines, electric flux density lines, they are normal to this surface and go away into the medium 1. So normal to the surface means n you got, into the medium 1 means suffix 1 you got. This normal component is generated from the rho s, that is why you got rho s here, and this is scalar, that is why you got mod here. So वो जो डेरिवेशन किया उसको भूल जाओ, ये पॉइंट्स याद रखो. Between dielectric and boundary conductor, out of 4 components, here tangential normal, here tangential normal, 3 are 0, but only normal component is present in medium 1 side. That means normal component is present outside the conductor. If rho s is there, if rho s is 0 on this, then that is also 0, nothing is there. So this is one point. This equation you have to remember. Next, on the